Hello. In this clip, I want to go over another programming example that involves the support vector machines, trees, pruned trees, and random forest in an example where we use synthetic data, meaning that we generate the data, and this is in contrast to the previous example where we used real data. In another example that we used before, um, we have been using the IMDb data set and also the sonar data, which was from this paper, which is available on Blackboard. Okay, but here this is a problem where we only have two features, and the point is that we want to get a little bit more intuitive insight into the inner workings of random forest. How is random forest and support vector machines different? Because it seems like both of them are super flexible. Okay, so in the first part, this code is available on Blackboard. The title is svm underscore 3 underscore in class R. In the first part, I remove any objects that exist in the memory. I also clear the screen, call the libraries we need, set the seed to 1 so that the results are reproducible, meaning that the random variables give me the random number generators give me the same sequence of number whenever I run this code, so I can compare the results of the code with previous runs. That's very useful for debugging. Now, 1,000 observations, 2 features. Here, Here we create a random matrix where we fill the entries with zero mean unit variate Gaussians. So the entries are independent, identically distributed, standard normals, zero mean unit variance. Q stands for the proportion of ones. So Q is the probability that y is 1 is Q, and the probability that y is -1, in this problem we work with 1 and -1, is 1 minus Q. Here we just create a sequence of n times 1 minus Q negative ones and the rest ones. So we create roughly a proportion of Q ones. O is 2. O is not here standard deviation, it's a factor that will become clear in a second what it does. Here we go over each row, and then we normalize each row. So what we do here is we divide each coordinate by the distance of that point from the origin. So geometrically, this is what's happening. Imagine we're in a two-dimensional space. vertical axis is x2, horizontal axis is x1, and then you have a point, an arbitrary point with an arbitrary x1 and x2. So it's a scalar here. x1 is a scalar, is the first coordinate of x, and x2 is the second coordinate. And then if we create a new variable, x1 tilde and x2 tilde, from x1 and x2, by dividing x1 by the square root of x1 square plus x2 square, and the same here, then what we're doing is that we're just creating a new point which is pointing in the same direction but whose distance from the origin is 1, because the square root of x1 square plus x2 square is 1. So here we first filled the matrix with just random variables. It doesn't matter really what they are, just uniformly spread around the origin here. So they're just scattered around here. But then when we divide them by these quantities, we all project them on the circle, the unit circle. So all these points will fall. It's as if we draw a random sample on this unit circle. And then for each observation, depending on whether the label was 1 or not, if it's 1, then what we do is we randomly take this point and either bring it closer to the origin or farther away from the origin. And the way we are doing it is this. We have this variable s, which here I call z tilde. So s is z tilde here. And r binomial 1, 1.5 is a random variable, which is 1 with probability half and 0 with probability half. So if you take this and then you subtract half and then multiply it by 2, we get a random variable which in the code is s. In the note it's z tilde, and it's for probability 0.5 it's 1, with probability 0.5 it's -1. So we created 1 and -1, and then we say, okay, o to the power of s. So with probability 0.5 it's o to the power of 1, with probability 0.5 it's o to the power of -1. O is 2, meaning that W here, imagine W is an arbitrary number. It's either, imagine W refers to the entries of the ith row of X. So W times O to the power of S is 2W if S is 1, and it's W over 2 if S is -1. So what we are doing here is, first we have these points that are all on this unit circle. And some of them have label 1, some of them label -1. And then if they had label 1, randomly we would either take this point and then bring it here, which is twice as far as this point from the origin, or we would bring it here in the middle, which is half as far from the origin. So we're creating a circle inside for the ones, and the circles outsides for the ones randomly. And then in the middle we have the negative ones. We do that, and then at the end we add some small noise around it, just scatter it around, just to add some noise, just so that it's not 3 clean circles. Actually, let's just make this 0 for now. Then here, let's ignore this part. This is to rotate everything 5 degrees. Okay. Okay. Then we create a data frame with X as whatever the features and Y as the labels. Then we can fit a polynomial SVM with kernel polynomial, degree 10 and coefficient 1. Or we can use the radial kernel, give it a range of cost and gamma, and then tune it. Let's do that. We also we can use the code we had developed to plot the cross-validation. Where the gammas are. And we have the costs. And then we just give this here. And let's look at this. Okay, so this is a SVM landscape. When we plot it, we see that there's some small values here and some small values here. So I think we can move towards increasing the X values, which are the cost, and also increasing the Y values, which are the gammas. So instead of starting from 1, now I would start from 5, 20, and then I would go 40, 80, 160, and here I would start from 10, then I'd go to 40, 160, 640, and I would run this part again. Okay, great. So here we're capturing something. You see the numbers here go up. That means that the Y values, we are already good at 640. We shouldn't go higher. Maybe we can even go, it shows that it's around, this is 160, this is 640, this is 40, this is 10. And this is cost 5, 10, 20, 40, sorry, 5, 10, 20, 40, 80, 60. I guess we can become a little more precise. Maybe we make this 5, 10, 30, 90, 180, and 5, 10, 20, 40, 80, 160, 320. And here, let's just do 1 like this. Okay, good. So you see, we have a clear minimum here, almost. I mean, these are also small, but yeah, let's just look at this. Another way of looking at it is using the summary. And we get an idea of the minimums are around 0.005. And there's some 0.45. So, okay, so I guess we're close. We found a reasonable landscape. Just to make sure, now I would make this a bit bigger by going a little bit smaller, 0.2 for example. I would add 1 here, and then 0.5, and then 1.25, and here I would go to 640 just to expand the scope, and here I would go to 160. This would take a little longer, but just to make sure that you're not missing anything. Okay, good. So you see, we have this minimum here. It's clearly here. There's a landscape, and it goes here along these parameters. So even if I would expand it, this would become clearer. And let's just expand it, I mean, just for the sake of curiosity. It's 0.625. 0.4, 320, and here we have 1080. Okay, so it's too expandable. It's here. We already found this. We found it. Anyway, so just run the whole thing while this is happening. Sorry. Okay, so again, here I wanted to illustrate, this is not necessary, it was too big, obviously, as we saw. I just wanted to illustrate that how to find this, how to make that decision about what range to look. It's exploratory, but you know what are you exploring for. You're exploring for a local minimum, a basin, where the error is smaller. And as I said before, the GLMnet does it for you when it's about lasso, ridge, or elastic net, but for other methods, it's not the case. You have to do it yourself, and it's pretty straightforward. So now we got the SVM, we fit a tree, we can fit a tree, we can plot the tree, and look at it to see how the tree looks. We can cross-validate the tree to prune it. To prune it meaning making the tree smaller than that overgrown tree, meaning pruning it, getting rid of some extra leaves by knowing what's the optimal size based on the minimum deviance, and then we prune it for that specific size. Then we can plot the pruned tree and add the labels. We can do random forest. Random forest is, well, if M3 is P, then we are doing bagging. Bagging means that at each stage we consider all the features. Here, it wouldn't make a huge difference between random forest and here it doesn't make a huge difference between random forest and bagging because the number of features is 2. So it's just meaningless to speak about the difference between random forest and bagging. They are more or less the same. Here we're creating a grid to cover the whole space within the range of values of the horizontal and vertical coordinates we have for x. Here we label them as x1 and x2. Here we create the predictions using the SVM fit. Here we create the predictions using the tree fit. And the tree fit gives us 1 and zeros, which we need to turn into 1 and negative ones, which we do by subtracting from 0.5 and multiplying by 2. The same for the prune tree is happening. And then here we do bagging prediction. Once we have the predictions from SVM, tree, prune tree, and bagging, then we create these data frames to plot the results. That's all. Okay, so let's go one by one. We already saw this. Yeah, we find the minimum somewhere here. If I wanted to create a proper heat map, I would spend some time, and that's something you should do. I've done it a lot. When I'm creating a presentation or when I write a paper, this is how I don't leave it like this. I will make these proper labels. This is Y should be labeled as gamma. This X should be labeled as cost. And then these 0, 2.55 should be labeled according to whatever the values are. So here we have 1.25, 2.55. I wouldn't put all of them, but if there are like 5 ticks, I would make them correspond to the actual values here. And then I would create this Z would be the SVM radial cross-validation error. A figure, this figure then will be an informative figure. Okay, so okay, we look at that, and we have the tree. So let's plot the tree. This is how the tree looks. This is an overgrown tree. We have 2 features. We need the labels, and then here we can see now this is the tree fit to our data. It's mostly based on x1, and then it becomes about x2, and then depending on where you end, you have 1, negative 1. Now for the prune tree will be small. Now the tree apparently is not very different from the pruned tree, because the optimal size is probably too big, too large. It's 13, so it happens. Then we have the random forest, and finally we have this plot. Okay, great. Okay, so this is a reasonable plot. As you can see, these labels are -1, inner and outer are 1. Sorry, this middle one is -1, inner and outer are 1. This is not linearly separable. When you create a bagging, a radial SVM, this is the prediction it gives us. So it's able to separate this, right? This region is red, meaning -1, which is the same. And then anything outside is green, which is 1. If you have a tree, it looks at it as a box, so as a square, because trees perform horizontal and vertical splits, right? The radial SVM doesn't. It's invariant under rotation. Bagging is made out of many trees, and they are more or less the same. So you see that there is not much difference here between bagging and pruned tree. Now let's add some noise here. Okay, here's some problem. You know, when we do this first line, x1 is changed. Therefore, the sum is changing. Therefore, what we need to do here is to create this first and foremost as the radius. Let's call it r, and then divide it by r. I think that's the correct thing that we wanted to do. And let me just show you what happens. You see these concentrations that are here. This doesn't look like a perfect circle, but now it will. This doesn't look like a circle. First of all, I want to look at this. But let's look at this first. Where is it? I don't know, sometimes you have this problem. Let me reset. Oh, okay, here it is. You see, we have these, so now it's a perfect circle. This is how we generated the data. And the radial SVM, it's radial, so it's perfectly fit for this. I mean, it's a real one, but trees are doing splits around horizontal and vertical axis, so they cannot really be rotation invariant. Now let's add some noise, so it's not such a perfect concentric circles. Oh, and I want also to look at the landscape. What? Seems like summary SVM fit. Sorry, tune SVM. Okay. Oh, okay, so it doesn't really matter much because the error is 0 for almost any cost because it's perfect. You see, for a radial kernel, these concentric, I mean, essentially, this is just makes it perfect. I mean, for any range of variables, it works. But if you add noise, things will change. This is a perfect. This is too good. So let's just add some noise. So you see now we have added noise. It's not as now the minimum is here. What I wanted to look at in particular. Sorry. So here's an example of how things will look. It's a comparison between radial SVM and tagging, and how to plot, and how to present results, and how to do prediction, etc., etc. All right. Thank you.